Hi, this is Ms. Cho on how to convert quadratic functions from standard form to vertex form. This is useful because sometimes you get quadratics in standard form that don't factor or aren't easy to factor. In that case, if you were able to put it in a vertex form, then you could just solve by undoing the order of operations and taking the square roots. I'm going to use a technique called completing the square, and I'm going to do this visually using algebra tiles. In this example, we have rewrite the equation y equals x squared plus 6x plus 11 in vertex form by completing the square. As you can see, we have different kinds of tiles. This blue one is our x squared tiles. It has a length and a width of x, so an area of x squared. This tile is our x because it has a length of x and a width of 1. And this yellow one has a length and a width of 1, so an area of 1. Each tile also has a red negative side, so we can use that to represent negative numbers. If I were to model this expression, x squared plus 6x plus 11, I would have 1 blue x squared, 6 green x's, and 11 yellow ones. And the question is, we want to rewrite this into vertex form, which looks like y is equal to a x minus h squared plus k. We're going to have to remake this into a square plus something else. Because the side length is x, I don't know how many ones will match, so I'm not going to add there. I can, however, do something like this. This length here is x plus 1, 2, 3, 4, 5. And then here I have x plus 1. And then I have these 6 loose ones here. So I now have a rectangle of x plus 5 and x plus 1. But it's not what I'm looking for because I want a square. Well, what if I tried 4? If I have 4 on the top, then I have x plus 4 and then x plus 2, and then I have 3 loose ones, which is still not a square because I have 2 different side lengths. But I realize I can get them both to have the same side length if I have x plus 3. So now I have x plus 3 squared plus 2. And we know that our a term from this original equation is 1, so that means our a is 1. Our h is negative 3. I have a square plus something extra. So our equation is y equals 1 times x plus 3 squared plus 2. Let's try a second example. Our second example is rewrite y equals x squared plus 8x plus 7 in vertex form by completing the square. If I were to model this, I would have 1 blue x squared, 8 green x's, and 7 yellow ones. To make this a square, I have to have the same number of x's on the top and on the left. So I'm going to split my 8 x's into 2 groups, so 4 on the top and 4 on the left. Now I have x plus 4 on the top, x plus 4 on the side, so my side lengths are even, but I'm missing tiles on the inside, on the ones. I'm supposed to have 4 times 4, or 16, but I'm missing 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm missing 9 tiles, which tells me that my equation in vertex form is y equals x plus 4 squared minus 9. To summarize, when you complete the square with algebra tiles, first you have to make sure that a is equal to 1. This technique doesn't really work for leading coefficients other than 1, so your equation needs to be in the form x squared plus bx plus c. Your second step is to model or draw your trinomial with the tiles. You'll have 1x squared, you'll have some x's, which could be positive or negative, and you'll have some 1's. Your third step is to make a square with your tiles. To do that, you will have to split these in half. Your fourth step is to figure out how many units you're supposed to have. So this square would be b over 2 times b over 2, or b squared over 4. Your fifth step is to count how many extra or how many missing tiles you have in this corner. From there, your vertex form will look something like y is equal to x plus b over 2 squared plus some k, which are your missing or your extra tiles.